I don't see. This is, I think, the max you can have. And in order to add the pages, you need to add the pages. Okay, page 1, page 2, and so on. Fine. So let us do. So yesterday we were looking at our cascode, and we discussed the concepts of cascode mirror, cascode amplifier. We also looked at basically the cascode load. You know, when you're having amplifier with cascode load, what is happening, and it can be used for very high gain in a single stage. And then we looked at the cascode mirrors. There we looked at reduced swing cascode, where you have basically better output swing, or basically it can tolerate lower voltages. So those things also we discussed. So if you have any question before we proceed further, you can ask now before we go to the next topic. Briefly, I think frequency response, etc., were also discussed. So still, if you have any question, you can let me know right now before we proceed further. Any question before we continue? I have not basically given you any assignment so far. I thought of sending something yesterday, but I have not. So maybe today I will send you assignment based on whatever discussions we have today. So the two modules that are left, and I would like to complete, is the common gate and the common drain, so that we have at least the single-ended building blocks ready with us. So far, we have only looked at common source. We have looked at the variations of common source, different kinds of loads. We have looked at the cascode load, and there also we have arrived at high gain common source amplifier with cascode load. We also looked at folded cascode. So single-ended amplifiers we have looked at. Basically, we have looked at the variations of common source configuration. But the two other configurations also we need to visit quickly and analyze that, so that whenever there is a requirement, whenever these stages are required in our design, we can make use of that. So let us look at these two stages. So the first one is, say, common gate. So as the name suggests, we need to have, in this case, we are going to have our gate terminal common between the input and output port, and the input signal is going to be applied at the source. So this is the effective circuit. We can assume that, okay, there is a bias current for this, because ultimately when we apply so common gate, interestingly, can be used as a current to voltage amplifier and also a voltage to voltage amplifier. Now, when we use it as a current to voltage amplifier, the input is a current source and output is a voltage. And in other case, when you're looking at voltage to voltage amplifier, the input is going to be a voltage. So in both the cases, depending upon whether my input is current or voltage, I can have appropriate input conditions. So for example, now if we consider voltage to voltage amplifier, in that case, we can assume capacitive coupling. So this is a common gate amplifier where the input signal is being applied through, say, capacitive coupling. Suppose this is the input stage, and you are going off chip. This is your sensor signal V incoming, and there is a coupling capacitor. So we have discussed that in a common gate stage, you can apply the in a integrated circuit within the chip. You cannot apply big coupling capacitors, but when you're going off chip, very first interface with the external sensor, you can put a coupling capacitor. Assuming that is available, I am putting the CC, which is off chip capacitance. This is an off chip capacitor, and then the output is taken over here. V out is over here. This is RD. You call it M1, and gate. You can bias it. Suppose for the time being, I'm just biasing it using resistive divider, RG1, RG2. This is one possibility. And the second possibility is that your input is itself is current. Now, in case you are using it as a voltage amplifier, uh, we need to be aware of the input impedance, right? Because as opposed to common source, in this case, of course, you have a relatively smaller impedance, input impedance, right? What is R in? In this circuit, I want to find out that for my amplifier, what is the input impedance R in? What will be the expression for R in?
RD by GM.
RD by GM?
1 by
Sir,
GM plus
1 by GM.
1 by GM. Okay, so the exact expression we have seen. So if you look at R up parallel R down, right? So at this input node, we have impedance looking upward into the source and impedance of the current source. Current source, if I assume it is an ideal current source, it is simply infinite. So the impedance of the current source R down, this impedance is infinite. Only the upper segment is going to come into picture. And there, the exact expression we have anyway looked into, right? The exact expression is 1 upon GM1 plus the resistance in the drain, which is RD, divided by the intrinsic gain of the MOSFET GM1 RO1. So this is the, I don't know why this dot is coming every time. So when I'm writing one, this dot is, so ignore this dot. Is some artifact because of which this dot is coming. So different writing tools have different artifacts. So this one is having a strange artifact that it creates dot. Anyway, so going back. So GM, this is the expression for R in, right? This is your R in. And here, since it is a input signal is a voltage, we would like to basically have a larger R in. And therefore, you can, in this case, you can afford to have a larger RD as well, right? Because ultimately, you can have an active load also. You can have a larger RD value also. Again, RD gets limited only by the swing consideration. Uh, so for a voltage to voltage amplification, the only disadvantage here is that in case you are having a source which is having a large output resistance, R signal is large, then you do get a voltage division. And so if your V is over here and this is your uh, input device, because of the relatively lower input impedance, you will get a voltage division, and as a result, the overall signal at the output will also be resulting from this voltage division. So that is the issue with the common gate if you are using it as a voltage to voltage amplifier. So that all of us can understand. And the expression point of view, driving expression is not a big deal. So if you account for the R signal of the input source, and suppose this CC I can, for the time being, ignore. For the higher frequency, CC is absent, we can ignore it. And in that case, what is the how do we find out the overall gain? The first thing is we need to look at the signal appearing at the source of this common gate, right? So if you are able to find out what is the signal coming at this source Vs, then the overall voltage gain is known to us, because this is just like the common source amplifier. Only thing is the signal is being applied at the source and the gate is AC grounded. So you can assume that this gate is as a DC value, and in terms of AC it is going to be ground. And see, if you simulate this circuit just like this, you will still see that there is some signal coming at the gate. If you apply a signal at the input, and you are getting a good gain at the output, but this point will have some signal. It will not be AC ground. Why is that? Yes, why is that going to happen? Anyone? What I'm saying is, if you are just providing a DC bias with the help of RG1, RG2, and this is your VDD, this is your ground, and you have chosen RG1, RG2 appropriately to get a gate voltage. But what I'm saying is, if you apply a signal in this condition, you will still get, you will observe some, finite signals at the gate. You will get a good amount of signal fluctuation at the gate. Why it is happening? Why should it happen at all?
So because of the capacitors.
Yes. So you have the capacitors, right? So if you look at the coupling, this is called capacitive coupling. So you have an effective capacitance between the drain and the this particular gate node, and also you have a capacitance between the source and this node. And both these nodes, of course, they are oscillating in phase. Whatever is the signal, not oscillating. Whatever signal you have applied, it is getting amplified over here and coming at the source. Also, you have signal, and here you have a basically it's like a low pass filter, right? So if you look at this node, sorry, high pass filter. So this is CR. So you are basically going to get some signal. It is just like a CR circuit, CR output. But this node, ultimately, because of this CR combination, you are going to get some finite signal. It is not going to be zero. It is not going to be an ideal AC ground. So one way to make it a good AC ground would be that, okay, you put a large capacitor C bypass over here. So in that case, this AC fluctuation over here will be suppressed, and then you can treat this as a ideal ground. Otherwise, you will have this kind of AC signal coming at the gate. Uh, So for the time being in the analysis, we are assuming that this point is AC ground for simplicity. But just in case you are simulating this, you will observe signals at the gate that you should be aware of. So now, first of all, finding out the signal Vs, right? So how do we find out the signal Vs?
Sir, in this circuit, like we have the input voltage as well as the current source.
The current source is the DC current source. This is the DC bias. Because in order to operate the common gate amplifier, you need a bias, right? So this current source is just providing you the DC bias current for the common gate amplifier. There are other ways also you can do it. You can put a resistor over there also, and then also you can operate it as a common gate. For the time being, I have biased it using a DC current. So just like in common source, you can also insert a RS, and then the RS will determine RS, RG1, RG2 will determine what is the bias current, and then you apply the input signal. That is also one way, and the other way is you apply a DC bias current itself. So if you're given a DC calculation that, okay, this is the circuit, and you are having RG1, RG2 known, RG1, RG2, and VDD is known, VT is known, VT of this MOSFET is given, and you find out RS to get a current of 0.5 milliampere. This thing I think you can solve, right? So what is the RS value to get a 0.5 milliampere current? So given RG1, RG2 ratio, and you can find out RS. So that way you can, based on RG1, RG2 and RS, you can establish a DC bias, and then you can apply the input just like what we have done. And the other way is that you use a DC current source. So rather than using RS, you can basically connect a DC current source, which is coming from a current mirror, and this one goes there. So in that case, it is a current bias. So right now we just have a DC current source over here. Yes. So quickly, tell me what is the VS? How do we find out VS?
So it will be Rn divided by Rn plus R6 plus 1 by
Yes.
SCC.
The SCC we are ignoring. So here, assuming that frequency is sufficiently high, CC is bypassed. So in this case, this is just going to be voltage division. So here, if we look at this particular circuit, we need to see that, okay, what is the impedance of this circuit, right? So in order to find out the VS, the source signal, what is the signal coming at the source because of the applied input signal, we need to see what is the impedance coming up, above this line that I have drawn, above this partition, whatever circuit is present, what is the impedance offered by that. The DC current source anyways, assuming to be ideal, it is providing infinite impedance, so we can ignore that. But we need to record the impedance of the above circuit, which is already we have found out, 1 upon Gm plus RD upon Gm RO1. We can simplify it. We assume that it is just 1 upon Gm1, and your RD is much lower than RO1, then you can take it as 1 upon Gm1. So it is going to be just Rin upon Rin. See, this is a strange artifact. Wherever I'm writing small letters, it is giving me dot, 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 dot. So Rin plus R signal. See, whenever I'm writing I, it is creating dot. I tried 2-3 software. One of them is this one. So other software also have some other problem. This one is coming up with this problem. So this is your V. Yeah. So this much times V in is your VS. Now, once your VS is known, then the rest of the thing is simple, because for a common gate, for this particular configuration, if I know that the gate voltage is fixed, it is some AC ground, and you're applying a VS over here, and this is your output. So how do we find out what is the overall signal gain? So this is simple, right? This is common source. Just as compared to common source, the only thing is you have reversed the signal. It was earlier at the gate, source was grounded. Now it is at the source, gate is grounded. And therefore, we can, even without looking at the small signal model, we can write down what is going to be the small signal current. It is directly going to be GM VGS. And as a result, you are going to get the GM VGS current flowing through the resistor RD, and that is going to give you the polarity, the gain, which is equal to GM VS times RD. And here the polarity is positive, because if you are increasing the VS, what is happening? VGS is reducing, and if VGS reduces, the current in RD will reduce, and therefore the voltage will also go up. So if your VS goes up, current VGS reduces, and the overall current in the MOSFET goes up, and output signal goes up. That tells us, even without doing the small signal analysis, that this is a non-inverting amplifier, and you get a plus sign. And of course, you can draw the exact small signal model, and also you can do that. So this is the overall gain. And then you want to find out exact expression including RO. That also you can do, include RO and then solve, and that way also you can get it. So in this case, V out approximately equal to this expression, and VS we already know what is VS. So this is simple. So this is the overall small signal gain for the common gate amplifier. Now, in case you are using it as a current to voltage amplifier, which is called a transimpedance amplifier, then what will you do? So in this tool, I don't think there is, again, I tried to see whether there is any page break that I can introduce, but that doesn't happen. I don't think. No, that doesn't happen. So I'll have to just go to the new page. So if I'm using it as a current to voltage amplifier, that means transimpedance amplifier. That is another application. So now I can use it as a current to, what is going on? Current to voltage amplifier. Then you have this same condition. You can use the RG1, RG2, and you can use the bias current. And now you're going to have the AC current coming. So you can have an AC. You can still draw it as a AC current coming in, I in. And now in this case, once again, if you assume that this bias current is ideal, what is the gain? What is output signal? This is even simpler. If I assume that, again, now if this is a ideal, non-ideal source which also has R signal, so for a current source, how do we model the load, the source resistance? It comes in parallel. So if this has R signal, then of course you need to take into account the R in of the circuit, and the R in of the circuit we have already found out, right? So that is depending upon RD, whether RD is much greater than RO or much lower than RO, it is going to have that expression. So suppose we have that R in. So based on that, we can find out what is the signal going into the MOSFET, right? So here the DC current, anyway, if it is ideal, then this entire, the small signal current, whatever is available that to the MOSFET, that will be given by R signal upon R signal plus R in. And now we are going to have, this is your I going into the MOSFET, and therefore the output voltage is just directly going to be this times RD. Right? So output voltage, this is your V out. So in this case, V out, because whatever input signal current goes into the MOSFET, it comes out of the drain, right? So in this case, if you are looking at it as a current amplifier, current to voltage amplifier or transimpedance amplifier, whatever input signal current goes into the source, the same comes out of the drain, and therefore this times RD becomes your voltage. So this is the transimpedance amplifier configuration. In this case, of course, we would like to minimize Rin further so that most of the current goes into the MOSFET, and our signal does not basically reduce the signal received by the MOSFET. So it can be used in this configuration as well. So this is clear. So both the cases, one case it is being used as a voltage to voltage amplifier, and second one current to voltage amplifier. And one can understand that because of naturally it is having a lower input impedance, so the use of common gate as a current to voltage amplifier will be, I would say, more popular. And then the variations of this, although there are, when we study feedback, we will look at some of the variations, how you can apply feedback to make it even better. So this common gate amplifier is more popular for the current to voltage amplification, that we should definitely be convinced with. Now, looking at some other conditions, like if you talk about, say, uh, output signal swing and the bias voltages, etc., and the frequency response, those things also we should look at quickly. So looking at the output signal swing, output signal, if you look at, say, the gate voltage VG, which you have a fixed DC bias, and with respect to that, we understand that V out min is what? V out min is going to be equal to VG minus VT, right? That is determining my V out min, and V out max is what? It is approximately VDD, because upper side it can go all the way to VDD, lower side it will basically minimum value is dependent upon VG. So now in order to maximize the swing, what will I do? I will minimize this. Upper side anyway it is VDD, lower side it is VG minus VT. So in order to maximize the swing, I will try to minimize this quantity, and therefore I will try to minimize VG. What will VG depend upon?
Bias current.
Bias current means that is okay, but here what is the VG, like what is the minimum value of VG you can have?
W by L.
Yeah, so you have some VGS of this MOSFET, which is basically the VT plus V over drive of this MOSFET, and then you also have the output voltage requirement for this current source. So yesterday we have discussed two kinds of current sources, uh, where we have cascade as well as simple current source. So the current source will be giving you some, we have also got to, of course, minimize the voltage required by the current source, that is the voltage headroom consumed by the current source. So we use the terminology yesterday that this current source is going to have some voltage headroom. It requires some voltage headroom to operate. And we saw that if you're using a cascade current source, especially the reduced swing cascade, there it will be close to, say, 2V over drive. So there also we have some options. We can basically try to minimize that 2V over drive by increasing the sizes, etc. So that is one option. But again, we will see that it is, when we discuss the noise of the circuits, we will see that it is not that straightforward. If you increase the GM too much and decrease the W by L, if you also increase too much, it may create problem in terms of noise. For the time being, assume that, okay, you have gate voltage, basically, this is ultimately a current source which is having a headroom requirement of 2V over drive. So 2V over drive plus VGS. So these are the two components. So this VG is going to be what? It is going to be 2V over drive. This is the headroom of the current source plus VGS of this particular MOSFET, which is V over drive of M1 plus VT of M1. This is coming from the current mirror. This is from the current mirror. This is from the MOSFET. And then this thing can be minimized by W by L. So here, if you increase the W by L, you can reduce the required V over drive, and that way you can go for minimum VGS. Now, if you, of course, if you go on with increasing the W by L, you will have other issues, although you are probably able to reduce the impedance, but then also other thing, we have to look at the capacitance. So the overall frequency bandwidth required for the circuit will suffer if you increase the device size too much. That also you should be aware of. So both things we have to check. So now, of course, here we also have, so the RD, as I said, here if you're using, just like in common source, here also you're going to have direct, basically, trade-off between gain, the signal gain as well as the swing, right? So here your V out max and V out min, we have said that, okay, these are the values, V out max, VDD, and V out min is this. And then if you want to bias it midway, and you get, maximum swing, in that case, again, the RD will be limited by that maximum swing consideration. For max, symmetric swing, you can do that, right? Swing.
So I am not audible.
Hello, am I audible?
No, sir, we couldn't hear you for a minute. Like for a minute, we could not hear you.
So I was getting some connection. I think right now I got some message that. So right now I'm audible.
Yes, sir.
Hello. So
Yes,
till
sir.
what point, so I was talking about the swing. So the swing consideration, I was talking about already that, okay, you just like in common source, you have the swing and gain conflict over here. So if you're using RD, so if you want symmetric swing, then the RD conditions will be determined by the DC bias point at the output for max symmetric swing. So here I know what is V out max, what is V out min, and from there I can determine what is the R value for max symmetric swing. If I don't want max symmetric swing, in that case, I can basically maximize the gain required. So if you don't have, suppose input signal is very small and you just want to maximize the gain, symmetric swing will be required when you have, say, the signal which is fluctuate, basically swinging in both directions. So it is a bipolar signal. It is going plus minus both ways. So then you require symmetric swing, right? So uh, so that means that as compared to the DC bias current, your current here is going up and down in both directions. So suppose you have a condition that the current is, say, only going to be it is only going to sink current. That means if I talk about, if I assume that this is the direction of positive current, so it is always either 0 or some value I in. So if it is unipolar, that means 0 to I in, is only sinking current. This source is a sinking source where whenever the signal is coming, it is just drawing some current. It is never supplying current. So in that case, what is the situation? So in that case, the current is going to be basically just reducing the output voltage. It will never increase the output voltage, right? So if it is always sinking, so as compared to the DC bias point at the output, the voltage will go down. And when the signal is 0, there is no signal, it will be at the DC point. So in that case, I have to be careful because ultimately here, whenever I'm drawing the signal current, wherever the signal current is on, it is going to reduce the output voltage. And therefore, if it is too high, if the signal swing at the output is too high, if I'm making RD too high just to get more gain, it will lead to this transistor entering into triode region. On the other side, if it is the opposite scenario, that means it is negative. That means basically it is supplying the current. So supplying the current, in that case, we expect that ultimately the voltage will increase. So either it will remain at the DC point or it will increase. In that case, the scenario is just the opposite, right? So in that case, the scenario is that whatever DC point you have, as compared to that, the signal is only going to go up. So in that case, probably I can make RD to maximum possible. I don't need symmetric swing in that condition. The DC condition at the output will be such that I can just keep it close or basically just beyond the edge of saturation, so that ultimately when my signal is coming, it is only going to push the voltage at the drain up close to VDD. So that in that way, I will have the maximum swing. So whether you need maximum symmetric swing or not, that depends upon the input signal characteristics, right? So here we can see that the two cases, in one case signal current is being supplied, another case it is being sunk, the behavior is different. That also tells you that whether you want to use NMOS input device or PMOS input device. I can also make a common gate with PMOS input device. There the scenario will be different, right? So in that case, depending upon the current behavior or the source behavior, I can connect it in another way, and I can make a common gate with PMOS device. So that way, the scenario will be just reversed, right? So in this case, what we see is that if the signal is unipolar, that means it is going from zero to some max value, positive or negative. So in this case, the configuration here is good if the signal is going inside. That means the current is the source or the signal source is supplying current. In that case, if it is supplying current, that means ultimately you are going to get the voltage increasing. So therefore, I can bias it at the lower. And also in terms of current behavior, we should understand exactly what is happening. What do you mean when the signal is being supplied by the source? What do you mean when the signal is being uh, basically extracted from the source? So that also let us look at a little bit more detail. What is the transistor's behavior? So this is anyway VG, which is fixed, and you are assuming that this is a ideal current source. If it is not ideal, of course, we will look into that. Now, if this is a situation where you are saying that the current is being supplied, current is being supplied means what? So you have this DC current, which is always constant, it is not changing. And now if you are pushing additional current into this, that means whatever I in is there. So in this node, you're getting I in and you're getting IDC. So now this IDC must be whatever is your net current, because this is net current flowing down. This must be equal to I in plus whatever is the I1, or basically the, I would say, total current flowing into the MOSFET. So let me call it I1. So this is not just the AC, this is the total net current. I in 1 is the small signal current, and I1, suppose this is the net current of the MOSFET. So I1 plus I in must be equal to IDC. Now, if I in is positive, that means it is supplying current, and the total sum is positive over here. That means what does it mean? That I1 needs to reduce. That means the MOSFET current actually needs to reduce, so that I1 plus In should be equal to IDC. And if the MOSFET current is basically reducing, that means the voltage over here will go up, right? So that behavior we should understand what is happening in the MOSFET current. What is happening because of the signal polarity? If the signal polarity is opposite, that means it is extracting current. So then once again, the this is for the sourcing part, sourcing signal. That means the signal is sourcing current. And the opposite case, what will happen? You have I signal or I in plus IDC equal to I1. There is a MOSFET current. So this case, of course, we understand that if your signal is sinking current, this is your sinking, sorry, sinking signal K signal. So in this case, if your current is increasing, that means it is sinking current. You must be having the I1 increasing. And if the I1 increases, then only it will be able to support IDC plus this additional current. That means that additional current is actually adding to the MOSFET current, and therefore the voltage at the drain must go down. So we are seeing that ultimately, if you're using an NMOS device as the input of the common gate, which scenario it is better? So if your polarity of the current is such that it is sourcing, so for that case, the best condition will be that, okay, you use NMOS input device and let it basically source the current. If you use the PMOS version, the story will be just reversed. You can think of it. In that case, the in case of sinking signal, PMOS input device will work better. So all right, and then looking at, say, input impedance. So input impedance also, since it is directly related to RD, right? So we should also be aware that there is going to be a trade-off between input impedance and the gain of this stage, right? Because if you try to get uh, current to voltage gain, a good current to voltage gain, ultimately is dependent upon RD, because here the current to voltage gain is directly RD. If you use large RD, it will not only affect the bandwidth of the circuit, but it will also affect the input impedance. So that also we should know that RD, large RD, that means R in goes up, and also the bandwidth will go down. So you have a trade-off between the maximum and also you have the swing. So in case of bipolar signal, the swing will also go down. So you have basically the situation where RD is having conflict with the input impedance requirement, bandwidth requirement, and the swing requirement. Now let us quickly look at the maybe the swing consideration also. Sorry, the frequency response also. So where is the next page? Next page is okay. No, so next page is coming here. Oh, it is copied. I don't want to copy. I want a new page, but it is not giving me a new page. What is
So maybe
this?
you should click that page plus icon at the top.
Yeah, so that is there. Okay, so fine. So you have this thing. Now, if you talk about the frequency response again, and the other stories like, if you have active load versus this remains same, whatever we have studied in common source, different kinds of active load, diode connected, this, that, current source load, diode connected load, a mixture of both of those, cascode load, all those things. The moment you put cascode load, it will no longer be suitable for a current input because the impedance will go up. Input impedance will go up, right? That also you remember. The moment you put a cascode load in the drain, that means the input impedance will shoot up. It will become equal to RO, which is not going to be suitable for a trans impedance amplifier. Now, looking at the frequency response, especially you're talking about current source configuration. Let me still keep it, say, ideal current source, and your input is also current source. So we need to see that, okay, what are the critical poles in this particular configuration? Of course, this is AC ground. For the time being, we're assuming it to be AC ground. So let us put it at the ground. And first thing is that, okay, if your source is also having, so this is your AC source, and you are having I in over here, and the source is also having impedance R in over here, or R signal, whatever I should call it, R signal, R signal. In that case, I need to look at the net capacitance at this point and the input impedance also, because it is going to form a pole over here. So what is the input capacitance? In this case, what is going to contribute to input capacitance? So you can think of this. Yeah, so this current source will also be like a real current source, of course. So assuming that, okay, this is also like a transistor. So first thing is for M1, you have the CGS, because the G is anyway grounded, so there is no Miller effect because of CGS. So it will come as it is. And assuming that body is also grounded, so then you will get the CDB. If body and source are shorted, then you will not get that. So here the two capacitances that are coming because of the upper MOSFET are CGS1 plus CD CSB1. CSB1. Thing is that deleting. So deleting with the right click was easier. Here you have to select the rubber. So CGS1 plus CSB1, and then you are going to also get the capacitance because of the current source MOSFET. So its CGD as well as CDB will contribute, and generally these number will be lesser because CGS is generally the dominant. So the dominant contribution will be CGS. And in case the source itself is having its capacitance, generally many cases the source itself will provide its capacitance, so you need to include that also. So C signal, so plus C signal. So that will become the input capacitance, the net capacitance between this point and AC ground. And then we also know what is the net input impedance. So that gives you the RC time constant for this particular node. And likewise at the output node, if the RD is sufficiently large, we can have a dominant pole here as well. Because ultimately at the input node, at least we have one advantage, that if RD is not comparable to RO, or RD is not much larger than RO, till that condition, the input impedance is still going to be of the order of 1 upon Gm. Only case, even if RD is of the order of RO, we know that it is going to be R in is going to be still 2 upon Gm kind of. So input impedance will still remain low, provided the Gm of the input device is large. So at least at this point, we have advantage that your input impedance is large. If the C signal itself happens to be large, then this may happen to be the dominant pole. Now at the output node, you have the net impedance. If I look at it, what is the net impedance at the output node? Small signal resistance at the output node. Yes, quickly. What is the net small signal resistance at the output node?
So like if the current source we are considering that resistance also, then it will be like RD in parallel with 1 plus GMRO times RO of the current source.
Yeah, so we have looked into the case there. If you have a MOSFET, ultimately we are looking at the net impedance at this node, output impedance at this node. This is RD. So R up is RD. R down we have to find out. R down in this case is going to be what? This is ground. So R down is what? If I assume that is ideal current source, then it is gone. If you have a real current source, suppose it is RO giving you RO of the current source, and then you have the R signal. So ultimately, it will depend upon R signal, right? So R signal, if the R signal is uh, small, then the net impedance level becomes R signal. Then you have to consider it. If the R signal is very large, much larger than, or basically comparable to RO, then you can ignore it. So depending upon R signal, you will have to find out. So if the R signal is comparable to RO, then still that the impedance looking into the drain becomes GM1 RO1 times whatever is there in the source. So this RS is nothing else but R signal parallel RO. So depending upon the relative magnitudes of R signal and RO, you may derive it, and then you will get that. If it is comparable to RO, then this figure becomes much larger than RD, especially if RD is the passive resistance, and then the output resistance will be simply equal to RD. So R out, you can say that at the output node it is simply equal to RD, provided this R down is much larger. And as I said, it depends upon R signal. And then you have the net capacitance at this node, which is mostly given by CGD of this one, and CDB of the MOSFET, assuming that the body is AC ground. So in that case, the capacitances coming at this node are also relatively small, because remember CGD of MOSFET is significantly smaller than CGS. Likewise, CDB is further smaller. So these two capacitances are relatively smaller. And of course, next stage, if you have a next stage which is also being driven by this, then you need to look into the input capacitance of the next stage, so that you can capture as CL, whatever is the CL. So this plus CL. So then if the CL is large, then again, you may have to consider that and find out what is the pole. So it depends upon very much what is the loading condition, what is the next stage, and also what is the source resistance. So only based on those, you can figure out which is going to be the dominant pole. So directly we can't say that, okay, this is going to be the dominant pole. Depends upon the source resistance, and also depends upon the next stage impedance. It depends upon what RD you are putting, and so on. Is that clear? So there should not be much. If you're giving this circuit and you're trying to simulate this circuit, trying to increase the bandwidth, you should be able to understand that, okay, changing what parameter, changing RD, how is it affecting the bandwidth, increasing the MOSFET size, how it is affecting the bandwidth, and also looking at the board plot, what is the overall if you're getting two poles, for example, in the board plot, AC analysis give you two pole which are sufficiently separate. In that case, you will be able to see clearly that, okay, first pole is over here, and after that I'm getting a lower slope, and after second pole you're getting a much higher slope. So those things you will be able to observe, and then which one is dominant you can figure out there, that, okay, if you change RD, what is happening to the pole, which one is shifting. So by doing a little bit of experiment, you can figure out which one is dominant in the circuit. And so that basically gives you some information about the frequency response or the frequency behavior. And as I said, the trade-off is very clear in this circuit. The trade-off is between the gain, the swing, the overall bandwidth, and the input impedance. So in this case, the input impedance comes as an additional parameter, because for current input, I want a good input or small input impedance. So in common source, anyway, that was not a concern, but in common gate, that is a concern. So in the gain, bandwidth, and swing, we have another parameter now coming up, which is the input impedance, and you need to basically meet requirements for all these four. This is clear. Any question before we proceed further? Okay, so if we don't have any question, we can proceed further. Now, again, likewise, you can look at the noise consideration also, similar to what we had done for cascode stage. This is also, if you look at the noise consideration, we can look at in case we are looking at current source. So for current source, we need to have an input referred noise current, right? So if you're looking at if the input signal is voltage, then we will derive the equivalent noise voltage, input referred noise voltage. But if the signal is current, then we derive the input signal or input referred noise current. So for that, once again, we can look at the, you can replace this MOSFET, the current source, ideal current source, you can replace with a MOSFET. And this is having some VB. So suppose, this is bias AC ground, and this is also bias, this is also AC ground. So this is your VG1, this is your bias of the MOSFET of the current source. Ultimately, it is coming from a current mirror. So this can be VB. And then you have basically the input. You want to have the current input referred current source. So input referred current, I need to find out what is the net equivalent noise current at the input resulting from all these devices. So again, if you talk about, if I capture the noise of these MOSFETs at the gate, I can, put the contribution of the noise sources of these MOSFETs at their gates, and I can put the noise contribution of the current 4 kT upon R, the equivalent, noise spectral density of the resistor R, and then in this two MOSFETs, which one is going to contribute more to the output noise? Output, first of all, I have to find out the output noise voltage, right? So the approach here will be that in order to find out the input referred noise current, first of all, of course, I have removed the input current source. So input current source has been removed. And now because of the device noises, I find out what is the output voltage. If I find out the net output voltage, I just simply divide by the voltage to current gain that I am getting. And that basically gives me the input referred noise current. So in this case, which of these two transistors will contribute to the output noise more? Sorry?
Lower one side is higher gain because it's common source.
Yeah, so this is a common source kind of device, right? Because the source is shorted to ground, whereas this one is again a cascode device for this, current source analysis. Sorry, for the noise analysis. So for noise analysis, this is like a common source, which is basically going to directly, contribute to the output noise. So if I say VNG2 and this is your VNG1, so VNG1 square and 2 square. Let me write it 2 square because ultimately we express everything in terms of the mean square or the mean square of the spectral density. So let me call it square. It's also square. This is also ultimately the square of the IR or INR, whatever, INR square. So now this one, if you look at this, what is the output voltage or output noise voltage because of VNG2 square? Yes, quickly. What is the output voltage because of the M2? Noise voltage at output node because of the VNG2.
It's like
Quickly.
GM, this thing, VNG2 whole square into GM2.
Why nobody? I only remember two voices. One is, I need more voices. Other people, why do they not speak? I have not taken test also. So this is my mistake. I am not taking test regularly, and I have for last several days I have not given assignment also. So that is another, problem. So other people, I don't know whether they are attending, whether they are listening, whether they are understanding. Nothing. There are in a political party there is a spokesperson. It seems like for this class there are one or two spokesperson. They take the responsibility of speaking. Others are all chilling. So I don't want a spokesperson for the class. Other people can use also, open up a little bit. Yes, anybody else? Let me see what is the situation. How many? So first of all, of course, attendance has also dropped. I don't know how many are continuing. So let's see. I can see Bishwayan Sarkar. Bishwayan Sarkar, can you tell me? Bishwayan Sarkar. See. I don't know how many. So I can see only 4 people online. I don't know what others I'm seeing they're attending, but yeah. So I can see 23, 24. Some people have dropped out just now. Earlier it was 26, and some people have, after I started asking questions, some people have left. So Prakhar Mishra.
Sir, am I audible?
Yes.
Sir, the current will be VNG2 square into GM square, GM2 square, and then voltage drop will be, we will multiply by R square.
Okay, fine. At least I got some answer. All right. So I have the input, the small signal current provided by the M2 is simply GM2 square into VNG2 square. And then this small signal current directly flows into the resistance, because this is a cascode device. Whatever small signal current flows into the source, the same comes out of the drain, and therefore it goes into the R. So this into R square is going to the voltage because of this one. What is the output voltage because of the M1? So let me Subodh Kumar. Subodh Kumar. Subodh Kumar, can you answer?
Sir, the effective GM will be R RD upon GM upon 1 plus GM R out of M2, and then from, and the effective R out will be RD parallel RO1, and then sir that will be gain. So from there then VNG square times the gain.
Okay, so you have probably first part of the answer was correct. Second part of the answer is probably uh, not so correct. But anyway, so you are approximately, yeah, you are correct that you are getting a source regeneration over here. So for M2, whatever the, if I look at the input noise or the gate noise signal for M2, they can definitely see, just like in the case of cascode, this one is going to have a source regeneration, and that source regeneration resistance is nothing else but RO2, which is large, and therefore the gain from this VNG to output is going to be small, and therefore we can ignore it effectively. So if I write it down, it will be VNG1 square, and this times approximately 1 upon GM RS, right? So overall gain of this one is going to be R square upon 1 plus GM2 RS, which is basically nothing else but R. I hope I can select like this also. Yes. Yeah, so GM2 into R, sorry, GM1 into RO2 square whole square. So this is the gain, right? So GMRS into GM, of course. So GM1 square. So GMRD upon 1 plus GMRS square is the multiplication factor for VNG1 square. And again, if I assume that this quantity is much larger than 1 and R is much smaller than RO, so as compared to the contribution of the source, the current source, this contribution is going to be small, and therefore I can ignore it. And then also I have the contribution of the current source 4 kT by R also. So what is the contribution of this 4 kT by R into what?
So you're finding an equivalent output current noise, so it'll just stay the same, I think.
No, the voltage. Here I'm trying
So
summing up the voltage. So R square, right? Because this node and the net impedance is R up parallel R down. R up is just R. R down is much larger. We know that cascode device. So R out, R down is going to be GM RO square, GM times RO square. So that is going to be much larger. Looking into the drain downward, the impedance is GM 1 RO 1 RO 2. So that I can ignore, and therefore the output noise voltage because of this is going to be this. And then if I want to find out the input referred noise current, So what is the gain from the input if I have a input current? So as compared to the, so I can basically draw it like this. So if I have an input referred noise current, what is the gain from here to output approximately? It's simply R square, right? So input current to output is the gain is simply R square, because whatever, if I assume that this RO is much larger and the input impedance here is approximately 1 upon GM, R is also, much, it is not very comparable to RO, it is smaller than RO. The input impedance here is approximately 1 upon GM, therefore the entire current is going up, and therefore your output, voltage is simply I times R. Therefore the gain is simply R square. So the whole thing I can divide by R square to get the IN square. So the input referred noise current will be this entire expression divided by R square. I can ignore this one, and therefore I'm left with basically the first two, right? Sorry, the first one and the third one. This is clear?
Yes, sir.
And therefore we can see that the current source GM also needs to be minimized, right? So earlier when I discussed the swing part, there I discussed that you can't arbitrarily go on increasing the W by L of the current source in this case, and you can see the reason, right? So you are going to get VNG square plus 4KT by R. So here the VNG square will depend upon the GM of the lower MOSFET, right? 4KT gamma GM. Of course, you have the 1 upon F noise is also there. So you can also add up the 1 upon F noise. So K upon W, L, CO, X, and F. So this will be there. And therefore, the 1 upon F noise, if you increase W and L both, 1 upon F noise will be reduced. Therefore, it may be good to have a larger W and L. So both W and L, if it is increased, the 1 upon F noise component goes lower, or because it becomes smaller. Whereas if you talk about the thermal noise is dependent upon the GM of this current source. If the GM of the current source is increased for a given bias current, increasing the W by L. Why will we increase the W by L? We know that in order to maximize the swing or allow minimum possible voltage at the output, I need to basically increase the W by L of this current source. And if you do that, the GM will basically increase, and as a result, the input referred noise current will increase. And you want to keep this input referred noise current much smaller than the overall input signal. So input signal amplitude, whatever it is, as compared to that, you should keep it small. So that will.
So one question.
Yes.
So the input noise we found out, then we were dividing by R squared. Like, so how is it R squared? Like, could you explain one more time?
What is the current to voltage gain of this circuit? We have discussed the current to voltage gain, right? So this is the current to voltage amplifier, transimpedance amplifier. So putting a current source over there, we just figure out what is the gain, right? So what is the gain?
So that was like R signal by R signal plus R input and then into R.
Although this is right now we are looking at the ideal. So this is the, when you find out the input referred noise current, it will be assuming an ideal current source. So there you don't have R signal. So here we just find out for a standalone amplifier, what is the input referred noise current.
Okay, then it's just starting. Okay.
So basically this figure tells us that, okay, if you are connecting any input sensor and its amplitude is something, it is providing some amplitude as compared to that input signal amplitude, I must make sure that the input referred noise current is much smaller. And another thing that I think I have missed, I have not discussed, is that in order to get the input referred, the magnitude of the input referred noise current, the RMS value, we also need to integrate. So I think spectrum point of view, we have discussed that, okay, there is this 1 upon F curve, and then there is thermal, and there is a 1 upon F noise corner. So in order to get that, what is the net input referred noise current, whatever is the signal bandwidth, for that bandwidth we need to integrate, because this is your Vn square per hertz, right? And then when you integrate this entire curve, suppose this is the curve that we are interested in, signal bandwidth is from here to here. So this noise, Vm square per hertz, we need to integrate. Then we will get the within this entire bandwidth of interest, what is the noise contributed by the device, by the amplifier itself. So that concept also should be aware. Then whenever we are talking about the noise comparison, like as compared to the input signal, we will have to integrate and find out what is the net noise voltage, the RMS noise voltage coming at the input. So both quantities you will find in a literature or in a particular design statement. You may look at Vn square hertz curve also, or you will get the integrated noise also, which is RMS value of the noise that is obtained by integrating the noise curve, the noise response, or the input referred noise spectrum with respect to the frequency, whatever is the desired bandwidth. So this part tells us that okay, this source, etc. Also we have to be careful, especially in case of common gate. The source current, the noise of the source current is also going to be important. I hope that is clear. Any question before we proceed further? Okay, so going further, common gate point of view, we can discuss a few more things. Let's see. Active load, etc. You can understand. I don't think there is much of a difficulty. Same thing. So I will not spend time on that. I think for the time being, let's just keep it here. And then when we discuss some feedback concepts, then we will see that how this circuit can be useful for interesting feedback circuits where you can get a high performance as well as low input impedance. Impedance requirement in many circuits, maybe especially when you are having transimpedance amplifier, the input requirement, the input impedance requirement may be very low. So you may require, say, R in of 100 ohm or 50 ohm kind of. So in those cases, how to get this R in of 50 ohm, that also happens to be a challenge, and we will look into that. So we will see using special feedback techniques, how can we get a very low input impedance. Here, input impedance is still of the order of 1 upon GM, right? So we are able to do it around 1 upon GM. So 1 upon GM also, GM may be 1 milliampere per volt. So in that case, it is still kilo ohm. So you can't make GM too high, otherwise power consumption, etc., will go up, or if you are increasing the W by L, speed will go down. So just relying on this 1 upon GM may not be always a good idea. So there are other techniques like feedback, with the help of which in this particular circuit we can achieve much lower impedance, and these are actually used in many applications, especially high-speed communication circuits. These are used. There are two extremes. There are two extremes for this kind of circuit. One extreme is where the input signal strength is maybe large, but the bandwidth required is also very big. That means communication circuit, for example. So you're talking about communication circuit, this circuit. So one of the application is that it can be used as a receiver for optical signals. Optical signals, the way it works is you will have a photodiode, which is connected between VDD and the input of this receiver. So this is a common gate circuit, and then you have the current source, and is a photodiode, and there is optical receiver. Is optical link. Optical link, basically, we know that it communicates light pulses. So light pulses will be basically impinging on this photodiode, and proportional to the light intensity, it will create the current pulses. So if there are light pulses coming over here, the optical link, this photodiode will basically produce the proportional current magnitude, and this current is going to go into this one, and I need to convert this into voltage. Here in this case, the requirement of the data rate may be very high. It may be of the order of 1 Gbps. That means you have to deal with 1 to 2 Gbps or even higher, several Gbps of data. 1 10 nanometer you can't achieve very high. At max, what you can go is maybe 5 Gbps. There are, of course, if you do some special designs, some special techniques, feedback, etc., there you may be able to go to the maximum. Even 10, 20 people have achieved 10 Gbps. Also, people have achieved. Lower technology nodes, the achievable frequency goes up. So lower frequency nodes, lower technology nodes, people have been able to achieve even faster data rates. That is one example. In this case, the overall current in the diode that can be relatively large, maybe 0.1 milliampere all the way to 1 milliampere. So this can be the range, and it can be few milliamperes to start with. So if the current is large, suppose it is to start with, it is 2 milliampere. In that case, even a 500 ohm resistor over here will be able to give you, full 1 volt peak to peak swing, which is good enough. So you may not the amplification, the gain requirement may not be very high. Gain requirement may be just the RD requirement may not be very high. The main thing is you have to make it work for high frequency. It may have its own capacitance also, so it may have as high as 1 picofarad capacitance, and it may have its own effective resistance as well. So it may have, say, few kilo ohms of resistance, and then you have to model it as a current source, and you have to simulate, and you have to find out that, okay, what is the maximum bandwidth you are able to achieve. And this is one example. Another extreme case is low power circuit, low power biomedical circuit. There, people use photodiodes also for certain applications. There is one application which is called PPG, where there is again a use of photodiode. The idea over there is also simple. The way it works over there is same thing. The only thing is, first you have a LED source. So here there will be LED diode. So here they will be having a LED which is driven. So this LED is from the chip. So this LED, they will provide the drive current, and it will produce some light, and this falls on the skin. So basically you put your finger over there and it falls on the skin, and some part is reflected, and depending upon the blood velocity that you are having under your skin, the not velocity, depending upon the blood glucose level, the reflected light may have some shift in the amplitude and phase. So basically there is a Doppler kind of effect, because of which the light undergoes some shift. The light phase and amplitude may have some shift because of the blood flow just below the skin. And that basically, that change in amplitude has to be detected. That change in phase has to be detected. So for that, once again, the change becomes important. Here is not the absolute signal level, but we are trying to detect that small change. And that may be in the order of, say, 100 microampere or even smaller than that. So there, the noise consideration will become very important. The bandwidth will be very small. Maybe the data rate required over here, all the pulse with which you are driving this LED and receiving the signal, that may be very small, of the order of few kilohertz. But there, the noise consideration is a lot more important, because the signal may be a few tens of microampere to 200 microampere. So there, the noise consideration is much more important. Speed is not such a big thing, and gain is also very important. So gain becomes, I need a large gain, right? Because the input signal current is very small, or basically I have to basically detect only the difference. I have to, design the circuit so that it can detect a small difference or small change in the received current. And then your bandwidth is low, but the noise requirement is very tight. You need to have a very small noise. So depending upon the application, the overall, the circuit design may change. The circuit is same, but the specification, depending on the application, it will be very, very different. Is that clear to all of you? Any question before we proceed further? Okay, so if you don't have any question, we can proceed for, probably, this can be one of the assignment where you can club multiple amplifiers, including the common gate stage. Okay, so let us look at quickly the common drain stage also. That also you have already covered in your previous courses, but still we will go through some of the basics. Okay. So the common drain stage, also called source follower, Are you able to notice any improvement in the handwriting, or is it equally bad as compared to previous classes? Is there any change? Are you noticing any change? Yes.
I think it was fine either way. It's
Also,
not
sir.
hard in either of them.
Yes.
Like
No, but
before,
you are not able to see any change or any improvement.
it was fine either way. It's like,
Okay.
Improvement
So,
as it's not that visible.
sorry. I could not hear.
It
Yes,
was
ma'am.
fine before also. Sir.
Okay. So then why did I do such a, but yeah, for me writing is easier because I'm writing directly on the screen. So as compared to the earlier case. All right. So here I have more possibility of improving the handwriting rather than the previous case. Anyway, so that means my handwriting has not improved. So that is a bad thing. I have to still, although I have got the tool now, the better writing tool, but the handwriting, I need to be more careful. Okay, so we'll try. What is this one? This one is also a pen, right? This is a sketch pen. Okay. Okay, and I hope there is a bigger selection. We can select something or not. Selecting what? This is what. Anyway, so we'll figure out what is what. So let us go ahead. Common drain, as the name suggests, we are now going to have the drain terminal common between input and output. And if you're talking about the NMOS device, this is the input. Let me draw it other way, otherwise input will be a problem. Common between the input and output, and the output is taken at the source. So now here also we can start with an RS. Later we can replace it by a current source, and the input is being applied over here. This is VDD, and this is Vout. And conceptually, we can understand what is happening if you are uh, increasing the gate voltage. What is happening over here? You're trying to increase the current of the MOSFET when you are increasing the gate voltage. But when you increase that, once again, as the as the current increases, the source voltage also increases, and therefore VGS basically reduces, or basically does not increase as V in. So VGS is less than V in because source voltage is also increasing. So in terms of RS, we can determine what is going to be the exact behavior. If it is an ideal current source, if I replace RS by ideal current source, it is even easier to derive because if it is an ideal current source, the current does not change. So if the current does not change, and if you are changing the gate to source voltage, the only way, of course, there are two parameters. One is VDS and another one is VGS. But in this case, again, the VGS is changing. VG, you are trying to increase. So if I, for the time being, ignore the channel length modulation and you are increasing the VG, the source voltage should exactly follow the input voltage. So that is the best case, or basically ideal source follower example, where the source, basically, you are putting ideal current source or a good current source with very high output impedance, because in that case the source voltage will be exactly the replica of the input voltage. But if you have RS, if you have finite impedance, there also we need to look into account, take into account the finite impedance of the source, and for that we can again do the same analysis that we have done earlier. So we know that in this case the GM of this device, like as compared to the normal MOSFET, what is the GM of the device? You can figure out, right? Small signal model, you can draw and figure out what is the GM, because given input, the same, it is same as common source with source degeneration. So GM will be reduced by the same factor 1 plus GM RS, whatever is RS. And in case we are, the only issue is that if you are using current source then you need to take into account the RO also, because in this case, if your RS is very high, in that case, your RO comes in parallel, because RO is coming between source and the drain. And for accurate analysis, you can include the RS and RO in parallel because this is also AC ground. Here also you have AC ground. So both of these are ultimately AC grounds. RS also comes between the source and AC ground. RO also comes between source and AC ground. So if RS is getting comparable to RO, you need to include both of them. So all you can do is you can basically write down RS parallel RO.
Sir,
Yes.
so in this, we always use RS to be quite small though, right? That like this is used for a small output impedance.
Small output impedance is not given by RS, right? So we will come to that. Output impedance is what? So let us, this is okay, right? So you are convinced with this, GM is this is okay? Or,
Yes, sir.
you know, this, now
Impedance, we
this
also
is,
have GM in parallel, so it will be, that will make
sorry?
the impedance. So like this one, we
Yeah,
have
that is fine. So we will come to that. So now if this is clear, then for a given input signal, you have the small signal current produced is this, and therefore the output signal is simply GM, RS upon 1 plus GM RS parallel RO. Now, if I assume that RS is much greater than RO, and then I can simply cancel out, then that is the condition. Otherwise, I can take it RO here also. So if your RO RS are comparable, then ultimately it is coming in series, sorry, in parallel with RS. So I can, whatever small signal current is produced by the MOSFET, that will flow between the, or it will flow through the parallel combination of RS RO. So I can multiply it like this. And then if the denominator, if I assume that RS parallel RO times GM is much greater than 1, this will cancel out and will become approximately 1. So ultimately, here we see that it will depend upon this factor GM-RS. If the GM-RS is ensured to be much higher than 1, then the gain will be approximately 1, closer to 1. In case you are having RS finite and it is not so high, then it will basically not be exactly 1, it will reduce. As you reduce the RS, the overall gain will also reduce, it will become lower than 1. So this is one thing. So now, looking at the actual circuit, ultimately the way we bias is using the current source. So we use a current source with some bias voltage coming from current mirror, and the input signal is over here. And now we can figure out what is your output signal swing, etc. So now in this circuit, what is the output signal swing that we can have, maximum output signal swing? Or before that, we can also look at the input signal swing, because here that is more, I would say, but let us figure out what is the V out max and min first, and then we will go to the input. What is V out min? Quickly.
PV minus
I need other people to speak. I mean, why are others not speaking? If I was in a physical
VB
class,
minus VT.
sorry. Yes. What does the output mean? V out mean? Quickly.
it should be VB minus VT.
VB minus VT. Okay, fine. VB minus VT of 2, VT2. And the V out max? What is the maximum value of V out?
VNDC minus V threshold. Like so that the upper MOS is on.
Yeah. So remember that this earlier cases, what we have done regarding swing calculation is that we have not considered input swing so much, right? So common source, what do we say? That if you have to find out what is the minimum, so we say that, okay, as compared to the DC bias at the gate, it is going to be, this minimum is VG minus VT. Because what we assume is here the gain is much larger as compared to the signal swing at the output. Here the signal swing is very small, so I can basically ignore the signal swing here. Therefore, I simply write VG minus VT. Same thing for a common gate also, right? Here, however, the story is different. Here, output signal is almost same as input signal swing. So whatever swing we are getting here, same swing almost you are getting here. So I can't ignore the input signal swing as compared to output signal swing while looking at the swing consideration. So now, can you tell me what is the V out max? For V out max, I will have to find out what is the V in max. So what is the V in max? Because V out will follow V in. So what is the V in max?
Like VDD minus
V
plus V
In
threshold.
this circuit, V in can go all the way to VDD. Is there any problem? So if the V in goes to VDD, what is the problem? This MOSFET will still be in saturation. In fact, ideally it can go higher than VDD also. VDD plus, VT.
Yes.
So maximum voltage ideally is VDD. The gate voltage maximum allowed is VDD plus VT, assuming that you are limiting yourself to VDD. The V out max is V in max. V in max is actually VDD. Only thing, it will be limited by the previous stage. So previous stage may not be able to provide signal all the way to VDD because they have their own output voltage consideration. So we have seen that depending on whatever stage you have before that, it will have its own V out max, and that will provide what is the maximum signal level here, right? So that will give you what is the maximum signal. So corresponding to that, whatever is, suppose this is VDD for the time being, V out max over here will be what? Ultimately, you can size this transistor up. M1 you can keep it high so that the VGS becomes close to VT, and in that case, it is simply V out max is V in max, which is basically VDD, V in max minus VT. So that is the story. So in order to maximize the swing, I have two options. I can increase the W by L of M2, and I can also increase the W by L of M1. Both of them will basically help me in getting larger swing. That is okay. Now, if you talk about, say, output swing maximum, of course, here we are limited to, so as compared to the input signal, we are having a shift, right? So almost a VT shift, or slightly larger than VT, because VT plus V overdrive. So we are, as compared to the input level, we are having a slight shift in the signal. This is also like a level shifter. So it is providing a shift by almost VT of the M1. So if your input signal swing is, suppose this is 1.8 volt VDD, and this signal is, swinging from 1.6 all the way to, say, 1. Whatever, 1.4 or 1. Suppose 1.2. So this is a 400 millivolt peak to peak swing. And after shifting it down over here, this will be, suppose VT is 0.4, VT given is 0.4 volt is your VT. The signal levels at this point is expected to be what? This will be 1.2, and this will be 1.8. If your so ultimately, how low you can go, it will depend upon the VB. If your signal level over here goes too low, this VB will enter into triode region. So that also we have to be careful about, right?
So in maximum, how is it VDD? So like, want the MOS going to triode? Because like
Which MOSFET going to triode?
like M1 for M1, so how is V in max equal to VDD?
What is the triode region? What is the limit for maximum gate voltage over here for M1 to be in saturation?
Like it cannot be above VD by more than one threshold.
Yeah, so maximum is what? VDD plus VT. We are going only to VDD. What is the problem?
Okay.
So fine. So this is okay. So now I hope you understand what is the signal behavior of the circuit, how it is going to shift the signal, and lower side you may start getting clipping if you push the current source transistor into triode region. So these things you should be able to appreciate. Now let us look at impedance. So you said that, yeah, impedance. Somebody said that we need a good output impedance, or basically a low output impedance. So what is the small signal R out? Yeah, so sometimes, yeah, in textbooks, sometimes people follow a very strict rule that they will use small RO for small letters for R out, R in. Sometimes some books also use large letter. So I also keep mixing. Sometimes I use large letter, sometimes use small letter, but there's no such hard and fast rule. For the time being, suppose I use ROut. So what is the ROut in this circuit? So this is a common drain amplifier, and generally this is used as a buffer stage, and it is basically supposed to drive. It is supposed to provide a lower output impedance. Especially this is helpful when you are driving a large capacitive load or a small resistive load. So, for example, uh, ultimately we have seen that a good voltage to voltage amplifier or current to voltage amplifier, the moment your output port is a voltage. So we have four kinds of amplifier, and if the output port is a voltage, how do we model it? This is whatever k times V in. If this is the input, uh, you may have input port where you're applying V in. Output pole will be R out is the output impedance, and the k times V in, k is the gain. V in is applied input voltage. It can be a current to voltage amplifier also. So if the output port is voltage, this is how we model the output port. It is having a k times gain and output resistance. And now, if we want a good output, if we want a good current to voltage or voltage to voltage amplifier, what is the property of a good voltage source? Because this output is like a voltage source. So current to voltage amplifier or voltage to voltage amplifier, output port is a voltage source or like a voltage source. We want it to behave like a good voltage source. So what should the R out be?
As low as possible.
Low, sir.
As low as possible, close to zero. So therefore, whatever amplifiers we have discussed so far, whether it is common gate, common drain, cascode, all of them has large R out because that is only facilitating large gain. So the moment you want to have a good voltage to voltage amplifier, which can drive even low values of loads, the output gain should not depend upon the RL. So in those cases, we cannot directly connect the outputs of common gate or common source. We need to basically use this source follower to provide a low output impedance, and so that it can drive RL, low values of RL also. So how it is low? So what is the output impedance in this case? So this is a circuit, right? Right now the circuit is this. So if you have to find out the output impedance, what will you do? Input signal will be shunted to 0, and I will, this is the current source. Suppose I have the, replacing the current source by its impedance, which is RO, right? If this is the current source, what is the impedance looking into the drain? It is RO. And then you apply the test voltage over here, VT, find out what is IT. What is the impedance looking into the output?
RO parallel 1 by GM parallel RO of the MOS.
Yeah, so here looking upward, you have 1 upon GM of this MOSFET M1, and RO1 is also coming, as you said, between source and drain. That anyway we can ignore. And bottom side between this point and the ground, you have RO. So you are basically getting two ROs. So one RO is here also for this MOSFET. So this is also coming between source and AC ground. So the GM of this MOSFET, 1 upon GM looking into the source in parallel with 2 RO, I can ignore these 2 ROs and it will be approximately 1 upon GM. So which can be significantly lower than RO. So that is the advantage. So if you are making GM large, in that case, you can basically get a relatively smaller output impedance of few hundreds of ohms, right? Of the order of 100 ohms. So that is the benefit. So another, apart from driving low values of RL, another important consideration is when you have to drive a big capacitive load. So if you have a big capacitive load, many cases you may have to drive big capacitor, or the output is having a big capacitive load. So in that case also, if you don't have RL but a big capacitive load at the output, there also, what is the benefit of having low R out?
Bandwidth will be better.
Bandwidth will be better because ultimately in this case, if your R out is large, the overall RC time constant at this node will become very large, and as a result, the pole will be at very low frequency. It will limit the speed of the circuit. So the moment we have to drive large capacitive load, we may use common source, the common drain stage or the source follower stage. So both for low output impedance, this low output impedance is beneficial for both cases. Case one, you are supposed to drive low resistive load, the resistance load is small in value, or the input impedance of the next stage is small, or large capacitive load. In both cases, common drain stage can be used. Any questions before we proceed further? So let us do some more analysis for this. Say frequency response. I can use an ideal current source that will simplify some analysis for the time being. Let us keep it, and then you have the input side. So now in this case, if I use, suppose this current source is pretty good, you're using cascode current source, etc., providing very large output impedance, fine. Now you have a voltage source. Now this is a whatever common source, common gate amplifier, which is having a large R out, sufficiently large R out, and this is your V in, or rather I should not call it R out, it will confuse you. So this is a R signal. So previous stage can be anything. It can be common gate, common drain, cascode, whatever. So which is providing a signal which is large signal sufficiently, and you are also getting basically R signal which is large. So definitely I need to be concerned about the capacitance at this node, because this R signal can be large. So this is going to give me one critical pole, and also we need to look at this particular point. This particular point, as we have already seen, if the capacitive load here is large, then of course it will be of concern, serious concern. Otherwise, if the capacitive load here is very small, we may not be very worried. Why? Because in this case, your impedance at this node, small signal resistance, is just 1 upon GM, right? So R, if I call this say R out is close to 1 upon GM. So if you don't have a very large capacitive load, the overall RC time constant at this node may not be very large. And this may be the dominant pole. Now, if I look at this, what is the net capacitance coming? So one is the CGS between gate and source, another is the CGD. CGD comes as it is because this is AC ground. The VDD is AC ground. CGD comes as it is. What about CGS? I am trying to find out the,
So
what is
it's
CGS?
Basically,
sort
we
of-
remove.
it's not there, yeah.
Sorry?
CGS is not there.
You
Like
can
that
neglect CGS.
is one, so it's not
Yes,
there.
so same as our earlier stage, right? So earlier case also, in the case of source degeneration resistance, we have seen the moment you are having the source voltage following the gate voltage. If it's the ideal current source, it is more exact, right? It is closer to the situation where source is exactly following the gate. So if you increase the gate voltage, source voltage also increases. Therefore, the voltage across CGS will not change. Voltage across CGS does not change, means that means it is not changing the stored charge across CGS. If it is not changing the stored charge across CGS, that means input current, whatever is coming, it will not take anything from it. It will always remain, the charge across CGS always remains almost fixed, and it is not taking any charge from the input. So therefore, you can forget about it. So CGS you can ignore on this side. And if you have to do the exact calculation, you can find out what is the gain from this point to this point, and in that case, it will become 1 minus A times CGS. And this 1 minus A is what A is close to 1, but in reality, it is always less than 1. So a number alpha which is less than 1 or closer to 1. It may be 0.9, whatever. Okay, so in this case, CGD is the major contributor. If CGS is very large, then even 0.1 times this may become significant. So you have to account for both of them. At least the Miller effect is not bad. Miller effect is not coming because anyway the gain is 1 from one point to another. Now, what about the second node at this particular point? What is the situation?
CSB and CDB are there.
Okay,
They're
so
very
body terminal, assuming that is AC ground, and I have the current source. If I assume, okay, the current source is a real current source, and it will have also its these two capacitance. So CGS of M2, call it M2 CGS, because this is AC ground. The current source, if I have the current source like this, whatever. So this part is a reference branch, and generally we assume that this is the AC ground. If you put a cap over here, big cap, then becomes more ideal, more close to AC ground. Otherwise, in reality, it does have some fluctuation. But for all simple analysis, we assume that okay, this is AC ground. Because this part is connected to the circuit, your common drain transistor is coming over here, and signal is coming over here. This is the output. So this is your current source. This M2 is your current source. M1 is your input device. So this is the scenario, and the second is the M2's CGD is going to contribute and CDB is going to contribute, because both of them are coming as gap between output node and AC ground. Fine, that I can add. And then upper device, we do have the CSB of the M1, right? That is going to come. M1, the body is also assumed that it is AC ground, and CSB is therefore coming into picture. Fine. So that gives us a net capacitance at the output point. And again, depending upon what is your load, what is the load capacitance. If the load capacitance is pretty large, then you will have to include it. If it is not, then these are the dominant capacitances. These are the contributors, and then you have whatever input capacitance you may have, you should include it. Whatever is the C load of the next stage, small or big, you need to include that. And then that multiplied by the overall small signal resistance here, which is 1 upon GM, gives you the net, basically, the net pole at this point, RC time constant at this point. One interesting effect that is applicable here, if you find out the contribution of CGS at this node, what will be the value? Exact, if I take into account the Miller effect, CGS effect at this node, what will be the value?
CGS into 1 by GM by RO plus 1 by GM.
1 minus 1 upon A into CGS, right? At this node, if I break the Miller capacitance and I take that 1 minus 1 upon A component, right? So it will be 1 minus 1 upon A times CGS. What is this value?
It is a negative value.
It's a negative value because A is lower than 1 minus 1 upon 0.8, 0.9, whatever, CGS. And therefore, it is going to give you something negative, right? Minus 0.2 by 0.8 times CGS. What does a negative CGS mean? Negative CGS means what is the impedance? 1 upon iota omega C. So if the C is negative, what does it mean? Minus C naught. Minus iota means what? Iota upon omega C naught.
90 degrees.
So this is acting like inductor, right? So inductor is having iota omega L. So here it is giving you a positive phase rather than 1 upon iota omega. It is giving you 1 plus iota upon the value. So this is a phenomena called inductive peaking for common drain. So basically, what will be the effect? Effectively, what is it doing? If it is a effective negative capacitance, it will cancel out from other capacitances. So it will effectively reduce the time constant at this node and enhance the bandwidth. So at certain frequency, when the effect of this capacitance becomes very visible, it will basically cancel out the effect of some other capacitances, and it leads to a peaking in the frequency response. So you may get a peaking behavior at some frequencies that comes because of this inductive peaking. And this phenomena itself is called inductive peaking.
And
And
what will be the
this
frequency at which this inductive peaking happens?
That will depend upon, again, other capacitances in the load capacitance. If the load capacitance is dominant in this case, it will be visible only at very high frequencies, close to the roll-off point, because the effect of this is because it is a lower capacitance, small value of capacitance. So effectively, its value, its impedance starts playing a role at higher frequencies. So this becomes very important when we are talking about feedback circuits and operational amplifier circuits. There we will see, when you try to simulate this behavior, closed loop behavior, we will look at the response of this inductive peaking and what is the effect it has in the stability, etc. So in the frequency response that is going to come in our multi-stage amplifier, whenever you are using common drain, this kind of peaking behavior may be observed. Effectively, this is because of the negative effective C value coming into picture. So in case you are doing this circuit analysis and you observe this kind of kink somewhere, it is attributable to this particular phenomena.
So the peaking,
Uh,
like using it for like oscillators, like in our third semester, like for fourth semester for oscillators, like Greenbridge oscillator also had like a peaking kind of frequency response.
that picking is different. There we are talking about closed loop circuit where you have you are basically having a overall loop gain. You want to keep the loop gain high, and you are having a peak in the response overall. This is not a closed loop circuit. This is open loop circuit. When you do the closed loop analysis, when you are using it as a feedback amplifier, and this is the output stage of the amplifier, there it becomes closed loop, and then the stability behavior, we need to take care of this inductive peaking, and we need to compensate for this kind of inductive peaking, make sure that it is not affecting the stability of the loop. So when we study the closed loop feedback amplifier, operation amplifier, there we will look at it in more detail. Is that clear? Okay, so I think common drain, these are the things that you should, noise point of view also, if you see ultimately you have the similar conditions. So the tail current source also similar behavior you will get. If you want to say the input referred noise voltage, uh, similar thing, right? Because this knows whatever noise voltage is coming over here like a common source, and therefore output at this point, of course, the overall impedance is 1 upon GM only, but still this point is going, this M2 is going to have a major contribution. We talk about this one, whatever noise voltage it has, again it has the source degeneration, so this may not have a serious contribution, but current source transistor will have a more serious contribution. So if you increase the GM of this M2 too much in order to increase the swing or increase the current, then you will basically also degrade some of the noise performance. But generally, noise performance may not be so serious for this stage, because generally this is being used for a common drain stage, and this is already receiving high input signal. So in general, for most cases, we may not worry too much about noise. In some special cases where the we are talking about very precise timing signal, clock signals, etc., there these noises may become important. But if you're talking about just normal analog signals, there the noise will not be important. So yeah, means there is a concept of phase noise that we will discuss at some point of time. If you're talking about phase noise of clocks, etc., and then you're using drivers like this in the circuit path, there even for these stages noise will become important. But for normal analog signals, it may not be important. This part will be discussed a little later. Mm, and then, if you talk about, say, we have discussed the speed, sizing point of view, bandwidth. Anyway, we have discussed voltage gain, etc. What is in this case? Do we, yeah, bias current, etc. Also, you understand that if you want to get closer and closer to that ideal value of gain 1, uh, you want to have lower and lower output impedance, then GM1 must be made high. So for that you have two options, W by L of the input device as well as the current. So this stage, if you burn a lot of current, bias current is high, you may achieve good GM that may translate to better output impedance, that means lower value of output impedance, and also your lower output impedance as well as better gain, closer to unity gain. But again, power dissipation will be a constraint. So generally, output stages of the amplifier, we try to provide larger bias current for this purpose in order to make the GM large and output impedance low, as well as the gain closer to unity. So those things also you should be aware of. Fine. It may happen that in some low power application, if you reduce the current too much, the 1 upon GM itself becomes large, means it's no longer very small value, and you're not getting the right kind of output impedance. So those things, again, the two parameters you should be aware of, very simple, W by L and ID, W by L of the input device and the bias current. Okay, and it is good to improve the RO of this device. M2, if the RO is good, then the gain is closer to unity. Okay, so any question before we proceed? So I think common gate, common drain, common source, all have been discussed. Cascode also has been discussed. So single-ended, more or less we have covered. Any question before we conclude further? Before we conclude? Yes, any question? So one assignment that I am thinking of, and I will post it. which may include this kind of circuits, because you have done single-ended, so that should basically cover some design effort on the single-ended side. So since we have covered these two examples, like one case we have looked at the common gate amplifier with input impedance with for a very high speed signal, and another case for very low speed signal. So let us start with a very high speed signal case. So that may be a good example, and let us try to make it a little bit more challenging. So assuming that you are using RD, I can use RD, or I can also use a dial connected load. If you use, again, it will have its own impedance. So you have to basically go for this condition, and here you are having a sourcing load. That means the current source that you're providing, this is a AC current source, and or you can have a pulse current source, I pulse. You use I pulse. That will be going from 0 to some value, 0 to some high value. And the peak to peak amplitude of this one, you can keep it maybe 100 micro ampere. And here you are supposed to get the bias current of this one. It has to be some appropriate value. You need to think about how to set the I bias that we have already discussed in the class, but right now, based on the discussion, you can figure out, and the value of RD. And of course, here you will have the right kind of biasing circuitry. You can use, for the time being, whatever, RG1, RG2. And this one will be a current mirror. So you can use a current mirror. Here you will have a reference current, so whatever current you want to put, IREF. And then you also need a input impedance. So here I am putting a input capacitance of 0.5 picofarad. This is 0.5 picofarad input capacitance. And the input resistance of this one is, say, what? Suppose 2 kilo. I'm trying to make it a little challenging. So 2 kilo, and this is 0.5 picofarad. And this is the source. And then you have basically, you need to operate this circuit at least till 1 gigahertz input signal. That means the pulse, it will be 1 Gbps. And then you also need to basically convert it into full swing. The output voltage should be full swing, VDD here. Now after this, whatever signal you are getting over here depend upon RD. The Rin, again, you would like to limit, right? So Rin will be, in this case, you can try to limit this Rin to at least, say, 1 kilo ohm or lower. Suppose I keep it 500 ohm. So my specification I'm giving you, Rin 500 ohm, which may not be difficult. This Rin you can easily achieve. I think. If I make it much lower, 100 ohm, then it will be challenging. But 500 should be doable. So Rin is 500. Bandwidth you are seeing 1 giga. You can maximize the bandwidth. So the challenge will be that whatever maximum you can get. Bias current, whatever total bias current in all these circuits. You can also, after this, you can use another amplification stage also, and you can limit the gain of this stage. You can use another stage also, which can be either a common source or a common. You can have a common source stage also at this particular point, depending upon the bias condition that you are providing. If it is a RD and the bias voltage over here, it is remaining closer to, as I said, this is a condition where input current is it is sourcing, so it is going up. So if your input current is going up, as I have said, up means what? Ultimately, it is going to reduce the current, and output will go all the way to VDD. So ultimately, the biasing condition in this, you have to put such that the if you want to maximize the swing at this stage and try to get the entire gain at this stage alone, that will be a different scenario. There you will try to maximize RD and bias this transistor at the edge of saturation. And if that is creating problem in the bandwidth, then you can insert another stage, which can be a common source stage. And here, whether you will use a common gate stage whether you will use a PMOS input device or a NMOS input device. If it is a common source stage, that also we need to decide. So here, depending upon the bias condition, if it is suppose relatively the DC point itself is lower, then you can use just a minute. Then you can use basically NMOS stage. The DC bias point that you are keeping over here is relatively higher. You can use a PMOS stage. You can also use the circuit that we had discussed the other day, right? Yesterday we discussed this particular circuit, which can also achieve a good gain. Basically, it can give you almost full swing output. So this particular thing, you will have to find out what is the R value. And if you do this, then only problem is that the DC bias at this particular point will become coupled. So whatever DC bias you are having here and here, ultimately it will get coupled to the DC bias at this point. So then these values, whatever your R2 you are using over here and whatever RD you are using over here, R2 again, if you're at the moment you are basically shorting the input output of this one, you will basically have a voltage division between this resistance and this resistance. So the DC biasing will be a little challenging. Alternatively, you can use a common source amplifier. In that case, it will be simply a common source stage, and you can use a direct connected load to get some additional gain. And then at this point, you have to obtain almost close to full swing. That means because it's ultimately a digital signal, it has to be converted into full swing signal. And then basically you can use a digital inverter to get the digital output over here. So this is what you have to do. So 3 stages. First stage is the common gate, which is basically transimpedance amplifier. Second stage may be a relatively low gain stage, which is just providing additional gain. Here you can size it accordingly. You can use all those strategies, biasing strategy we discussed. You can use a current source in parallel. We discussed that concept also. If you want more gain, if you don't need it, then even direct connected MOSFET will be good enough. And then after that, at this point, the target is to get maximum possible swing while keeping these transistors almost in saturation. Then finally, the inverter should be giving you peak-to-peak digital output. So this thing you can try to complete, and the net currents that I have, I would like to minimize the overall current. So you have two figure of merit. Figure of merit is the F max, maximum. If the frequency is higher, your design is better, and also the power dissipation. If your power dissipation is lower, your design is better. So now you understand that power dissipation point of view, what are the things? Ultimately, you will need to reduce the bias current in all the stages, whether it is this stage, output stage. Output stage is anyway inverter, so there you may not have much of option, but still you can, depending upon the bandwidth requirement, because I'm giving you the speed estimate also. We are asking you to go all the way to a gigahertz. So you try to see that what is the maximum F max you can get and what is the minimum power dissipation you can have while targeting speed around this range. So again, I can give you the design flow exactly step by step, what is the flow. But given the discussion that we have had on all these stages, common gate, common source, etc., you can figure out how to do it. This stage, it is possible to use active load also. For example, in the common gate stage, I can also use our, direct connected load, right? You can use the direct connected load, and along with that, you can use a current source load. Sorry, current source load. So this is VB. This is current source. This can be biased with the help of current source, and your input signal is coming here. This is another current source over here, and this is with the help of VG resistor. You have established the VG, and now if you want additional gain, because this case stage may not be able to give you additional lot of gain because it's just given by 1/GM of this transistor, then you can use another stage of common source amplifier and try to get additional gain. That is also possible, and you can do this, and after that you can put an inverter. So try to you can also use another current mirror over here to get a high. Sorry, not this one. You can use you can try to enhance this stage gain also. Remember, we need to bias this also. So if you're using common source stages, we need to make sure that direct connected is being used. for the proper bias. And here once again you can use a additional current source so that overall gain from both these stages, common gate as well as common source, is increased. So this configuration is also okay. So try to, maybe this is easier for you because here the RD, coupling RD with the next stage, it will be slightly more challenging. This one is easier because you know that, okay, this stage, the bias point will be determined by the PMOS, and then next stage, anyway, I need to use PMOS as the input device. And here you can adjust, you can find out what is the value of bias current to be used, what is the value of this, what is the current I should use for diverting into this current source, what should be the current going into the direct connected one, what should be the GM of the direct connected one. This is what you can look at. So the challenge is you have to maximize the figure of merit, and these two numbers, F max you have to maximize, and power dissipation you have to minimize. You have to see that with what minimum. So at least keep this frequency in mind, that okay, for the time being, at least I have to meet 1 gigahertz. For that, what is the minimum power dissipation I can achieve? Is that clear to all of you?
Yes.
Any question? So this one you don't do. This one will be more challenging because here biasing consideration is difficult. This one is easier because here the biasing is straightforward. Only thing is the first stage you may not be able to get enough gain, and the sizing of this PMOS ultimately is going to determine what is the DC bias point over here. So this DC bias point, for that, if you want to keep it sufficiently midway, then also you need to really reduce the GM of this one very by a large factor. You need to keep W by L very small so that the GM of this one is small, and the overall DC point over here is low. So those things you will have to still see. And whatever analysis we have done, it is based on ignoring RO. So when you actually take into account RO, you will see the effects coming. Like you will not get the ideal current source behavior. So those things you should be able to visualize. So many cases we have looked at the DC consideration, assuming ideal current source behavior. Like in even this kind of load, we have said that the moment you connect, this particular load, okay, current source in parallel with that connected load. So here we have assumed that this is acting like an ideal current source. So if you bias it with some IB, it will exactly take that IB, and the rest of the I tail current minus IB will go into that. That may not happen exactly. It will be having some difference because of channel length modulation. So those things you should be aware of. So I think you get started on this, and it should not take much time. It's a small circuit only.
So any gain specifications are like we have 0 to 100 microampere at the input.
So I've already told you that the output you need full swing. So here the gain should be, you should be able to derive that, okay, here I need almost full swing at the inverter output. So what signal over here will give you full swing? If you go few hundred millivolt for this inverter over here, it will give you close to full swing. So here we are assuming that it will be, maybe assume that, okay, it is already at this point, it is 500 millivolt peak to peak at least, or maybe more than that. Is that clear? So overall, what is it coming? 100 microampere, you're trying to convert it into almost 1 volt peak to peak at the second stage. So 10 to the power of 4 kind of gain, and that you have to get using these two stages. So you can figure out how much. So based on it may be challenging because if you use direct connected load, of course, it will be more challenging. If you, for example, you can in the first stage, if you use say a very in order to get a gain of maybe 10, you can so 10 to 15 gain still achievable using this kind of configuration. So 10 10 100 few hundred you can go. 10 to the power of 4 you will have to basically because you're using 100 microampere, and then you may have to use more amplification stages. That is also possible. For example, this stage itself, you can, in this case, you can apply a large R and try to get additional gain from here. So that is also another possibility. Otherwise, just insert another amplification stage. That is also okay. But the problem here will be that if you use common source stage, you are basically, you can't use just active load directly. Either you have to use RD or you have to use direct connected load in parallel with current source to get a proper bias. So that you have to be careful about. Um, if you want to use um, only RD over here, then only thing is that okay, whatever the DC point over here, you should be using it properly and decide that based on the DC bias point what is the go from 0 to 100 microampere. In that case, as we have said, we would like to keep the DC point over here pretty low, and then you have to apply it to a ultimately it is going to be VG minus close to maybe VG minus VT kind of, if you are achieving large gain. If the gain if the gain of this stage is limited, means because of the impedance requirement your gain is getting limited, then anyway you will not be able to achieve that gain. RD will be smaller, and then according to that, whatever RD you are getting and whatever DC point you are getting, you will have to basically make sure that the next stage is biased properly. If the next stage is not getting biased properly, you can take help of shift level shifters, common drain amplifier to shift the level up or down. That is also possible. Is that clear? So it is possible that in between you put a common drain and then shift the levels down. That is also possible. Is that clear? Any questions? So of course this is a lot of variables in this thing, and I have given you free hand on this. Only two constraints I have put that okay, in the input side I have given you some parameters that parasitic capacitance of the source is 0.5 picofarad, output impedance is 2 kilo ohm, current magnitude is 100 microampere, and the overall speed that you want to achieve is 100 1 giga at least, and the overall gain also but this is the overall gain you are getting. uh, Actually this is little aggressive. On source side I have given you some aggressive values. Generally it can this input current amplitude can be up to 1 milliampere also, especially for the diodes for communication purpose. And the capacitance value also have given you little aggressive. This can be 0.2 picofarad, but I am intentionally giving you more challenging, little bit more challenging, 0.5 and 100 micro. Let us try with that and see what you are getting. Is that clear? So many designs, if you'll see in literature, they are the quality of the design or how good the design is determined by figure of merit, and that is including some of the essential specifications. Like here, I have included two specifications: what is the F max and what is the power dissipation. And again, depending on application, you may have some other numbers also, like linearity or noise, etc., that we are not considering right now in this one. You can also have another challenge that okay, sometimes yes, any question?
So it's like possible like we could get a day off or something, like this will take like we need some time for this, and also we have some revisions pending for the previous topics to catch up.
Okay, you can get a day off.
Especially the cast part, like we have to cover some of that part, like for the theory part.
Code, I have you are I'm not applying it here, but anyway, you can do it.
So the gain part, I think it will be required, like because the common source stage I was getting maximum gain of around 15, 20, 10 to the power 4. I think by itself without cascode may not be possible.
No. So you have multiple stages over here. So cascode will not be possible because I am using the frequency required is very high. So common source you can still get large gain provided you use a very large impedance at the bias current is small. If you make it 0.1 micro or lower than that 50 micro, sorry, yeah, so 0.1 micro or not 0.1 micro, but I'm saying 0.1 milli below that, 50 micro, 10 micro current, bias current, and length, etc. is large, you can still get large gain in a single stage. Only thing is bandwidth will be limited. So here the challenge is bandwidth is also large, and you also need the input impedance. So here you are going to, well, here at least before the amplifier, if not 500, you need at least 100 millivolts so that this inverter can work properly. So if I assume that 100 millivolt at least, then 10 to the power of 5 gain, and for that also, sorry, 10 to the power of 3 gain, that also 10 to the power of 3 is not that challenging if you get say 30 gain 2 stages. it may be possible. And for 30-30, you will have to aggressively skew this W by L sizes, and you may have to use more than 2 stages. So here I'm giving only 2 stages. You may have to use more than that. So that is possible, because ultimately the speed is also important. You just can't increase the speed gain of individual stages. You have to achieve that high speed. So both these things have to be maximized. So that is.
And the MOS, we use that same model as before, right? The 180 nanometer.
Yes, 180 nanometer you can use.
Okay.
Okay, so in order to make your life easier, maybe I can make it 500 micro. Then it will be easy. Then it will be too easy. First you try with 500 micro, and then we will try to make it more challenging. Is that clear? 500 micro, I think even here, if you just ultimately the gain, if you see 500 micro, you need suppose 100 millivolt at the output of the first stage. So is it just basically 20 gains at this first stage? So that is this is achievable. So you can basically maybe in the first stage itself you can divide the gain such that first stage is giving you a gain of uh, 30, and for that if you use RD especially it will be very much possible. Only thing is you have to take care of bandwidth because you are requiring good bandwidth also. So try with 500 micro to start with. Is that okay? Yes, you said, so let us start with 500 micro. I will basically post this statement. So I will write it properly in a document and I will post it in the group. But conceptually, you have understood what is to be done. So first is a common gate stage. After that, in the input specification is given. What is the current and bias? What is the capacitance and what is the resistance of that current source? And then some of the signal strength is the signal frequency is given, and the gain requirement from 500 micro I have to go to say 500 millivolt peak to peak, 1000 still. For that 1000, if you need if you can do it in 3 stages, maybe we will require 2 more common throw stages. After this you can try to get maximum of the gain in the first stage. Whatever maximum gain you can get in the first stage you can try to get. For that you have to maximize RD while making sure that the input impedance is as per requirement, and also the swing is proper. Is that okay? Any question before we conclude? Yes. Anybody else? Anybody else having any question on this? I will document it properly. I will write it down nicely with all the requirements, and then I will give it to you. But I hope you understood what you have to do. So any question, you let me know. So you have all the tools for doing this. You have all the common the single stage amplifiers. You have common drain. The moment you want level shifting for interfacing 2 different stages, you can use common drain. You have common gate as the input. You can use common source for getting more amplification wherever required. All those things you can do. Even this amplifier that I'm writing, this one, can also be used as the input stage directly. That is also another option, because this also acts like a common transimpedance amplifier. But for the time being, let us start with common gate. Later we will look at another problem statement where you will use maybe this one also. For the time being, let us start with common gate. Common gate, common source.
So the input stage should generally have a high input. Okay. Oh, so this is the current source. Okay.
Yes. Fine. Again, today I also have 7:30 almost. I don't know how many are still alive on the link, how many are sleeping. Okay, so 20 people are still there. Okay, so any question before we conclude? And because many people have left, so it is better that you do individually. So I'm not sure, group point of view, if you do it 2 people per group, that is also okay. That is, if you still, I don't know how many are remaining. So the numbers have reduced to 20, 25 now. 25 people are coming. Earlier it was higher. We started with 50 people. Now it's 25 people. So I don't know how many will be doing, but those who are going to do it, if you want to do it in group, that is okay. I don't know how many of you still have your group members or how many have fled. So figure out, means if you have your group members intact, work with them and complete it. Otherwise, you want to do it alone, that is also okay. Any question before we conclude? Okay, so let us conclude then, and then I will basically write it clearly in a proper sheet, and I will give it to you for your virtual. And this, I think, one day is good enough. So tomorrow I can give you a break, and tomorrow, the day after tomorrow, by 2 p.m. you should be able to complete whatever you are able to do. Is that clear? In between, any doubt, etc., you can ask. You can always ping me, or you can post certain things in the group if you want. That is also okay. Is that clear? Any question before we conclude?
Like any off day, like do we have this week, just if possible?
I told you tomorrow you can take off day if you are so keen to take off day.
Okay.
Yes. So any question? I hope things, whatever I have covered so far, it is clear to all of you. So many things I have covered, which should have been covered in analog electronics, but what can be done? Any question before we conclude? Okay, if we don't have any question, let us conclude. Thank you.
Thank you, sir.
Thank you, sir.
Where is your?
Thank you.
Where is your?